take a look at example 3. This one's a little bit different because we don't have an equation to start off the problem. All of the other ones gave us this equation, and then we could take the derivative of that equation with respect to time, but we don't have an equation here. So part of the challenge of related rate problems is quite commonly there's no equation given, and we have to decide what equation can be used. They are usually geometry formulas. Some of the more common geometry formulas that you're going to see show up on related rate problems, you might want to write this down, are, let's see, the area of a circle equals pi r squared. The circumference of a circle equals 2 pi r. The area of a cylinder is equal to pi r squared height. It's basically a circle, see the pi r squared, stacked up to a certain height. Sorry, that would be the volume of a cylinder. I don't know why I wrote it that way. Weird. Volume of a cylinder is pi r squared height. The volume of a cone is super common, which would be 1/3 pi r squared height. That's because you can fit 3 cones into any cylinder. The volume of a sphere shows up often, 4/3 pi r cubed, as well as the surface area of a sphere, which should be 4 pi r squared. And then sometimes we use triangles. So it's common sometimes with triangles to use the area of a triangle, which would be 1/2 base times height, or sometimes the Pythagorean theorem for right triangles. A squared plus b squared equals c squared. It is possible to have some other ones, but these are the ones that show up the most. And so these are ones that you're going to want to be familiar with and be able to quickly reference and memorize before a test or a quiz. All right, number 3 says the radius of a circle. Okay, so we're probably going to be using circle formulas here. One of those or both of those. The radius of a circle is increasing at a rate, so we are talking about a derivative of 3 centimeters per minute. So the radius, r, has a rate of 3 centimeters per minute. Notice that the denominator here for the units is a time measurement, which is why I put t, dr over dt. We want to find the rate of change of the area of the circle. Well, area we represent with a capital A. This is still going to be with respect to time. And we want to do that specifically when the circumference is 48 degrees. Not degrees, 48 centimeters. Again, notice, no equation is given here. All right, so we are going to have to determine what equation we should be using in this problem. So when I'm looking at this problem, I often will kind of look at the find. What am I trying to find? I'm trying to find the rate of change of the area. Well, then I need an equation that references the area of the circle. So this is the equation I'm going to use. And I'm still going to do things in the same order that I did before. Now that I have an equation, I'm going to take the derivative of this equation, both sides, and I'm going to do this with respect to time. And then after that, I will use substitution in order to solve for what I'm looking for. So the derivative of a would be 1 times dA over dt, because we're doing this implicitly with respect to time, equals, well, pi is just a number. It's just a constant. This would be like 3x squared, same idea. I'm going to use power rule here, and I'll get 2 pi r times dr over dt. Okay, let's just geek out here for a minute. How cool is this? When you start with the area of a circle and you use the power rule, as part of that, you get the derivative of a circle. That is cool. That is way awesome. That is super cool. And it's going to be useful in the problem, but just enjoy the beauty of that for a moment. Okay, so moving on to the next step, I've done the derivative. So now I'm going to use substitution. dA over dt is what I'm trying to find. So that will remain my unknown quantity. 2 times pi. Oh, wait a minute. I don't know what r is, but I don't need to, because remember, this 48 pi is 2 pi r. So I can actually take our 48 centimeters. I could take this 48 and substitute it in for 2 pi r. And then this gets multiplied by dr over dt, which is 3. And so dA over dt is 144 units. I need the units. Well, this is always with respect to time if it starts off with respect to time for part of it. Okay, so these are with respect to time. But what should the units on the numerator be? Remember that we said that the circumference is measured in centimeters and the radius is measured in centimeters. The rate of change of the radius is centimeters per minute, so the radius itself is centimeters. Well, how do you measure area? Area is units squared. So this would be centimeters squared. There is actually one other way to figure that out. Back here from my derivative equation, the 2 pi r was my circumference, which was measured in centimeters. That was going to be multiplied by dr over dt, which is centimeters per minute. You can just use dimensional analysis here. This would be centimeters squared per minute when you multiply that. Oops, why did I write dt? Let's fix that. I want the actual unit of time. Lost my mind there. So the rate of change of the area with respect to time at the instant that the circumference is 48 is 144 centimeters squared per minute. So I'm going to encourage you to try number 4 on your own. Pause the video and give it a shot, and then restart it when either you're ready or if you get stuck. All right, on this problem, we want to find the rate of change of the volume of a cone. I am trying to find rate of change means derivative of the volume with respect to time. The radius is r, the height is h. Okay, that's normal, that's standard. dr over dt, the rate of change of the radius is 3 inches per minute. That's going to have some helpful information about units here. And h is equal to 2r, which is kind of cool for this particular cone. And we are looking specifically at the instant that the radius is 12 inches. Remember, derivatives are rates of change at an instant, not over an interval. So for this example, I want to be ultimately finding the rate of change of the volume of this cone. So if you know what you're trying to find, that can help you decide what formula you should be working with. We want to start off with the volume of the cone, so then I could take a derivative to find the rate of change of the volume. The formula for the volume of a cone is 1/3 pi r squared h. This is 1/3 of a cylinder's volume. Okay, right now I'm gonna recommend you don't write this next part down, but you just watch it. I want to show you a way to do this that would not be helpful, okay? And this usually just comes from a little bit lack of experience and not noticing some things. On the right side here, I would like you to notice that we have 2 different variables here being multiplied. If you're taking a derivative of this, you're going to have to use the product rule. If you take the derivative with the way it's currently written, you are going to have to use the product rule. That's not very exciting. And you'd have to use the product rule implicitly. No fun. And maybe not even possible to do that way. We may not have enough information. There are times where you can't avoid that. Yay, this is one of the times where you can avoid that, because they told us that h is equal to 2r. And so what I can do is I can rewrite this equation so that I have one less variable. I really don't like the 2 variables on the right-hand side being multiplied together. So I could either write this right-hand side in terms of h, or I could write it in terms of r. I'm going to say it's going to be easier to write it in terms of r and more useful because I have more information about r. So I might as well keep the variable r in the problem. And I'm going to rewrite this. I've not yet taken a derivative. I'm just trying to get this in a form that's more useful. And I'm going to replace h with 2r. And I'm going to just multiply this together since I do have the same variables, and that 2 is just a constant multiplier. And I can rewrite this as 2/3 pi r cubed. And now, on the right-hand side, I only have one variable. Remember, pi is not a variable. It is a constant. So this is now going to be much easier to take the derivative of. And you should, I'm sorry, I forgot to tell you, go and write this piece down. Go and write down how we replace the variable. I didn't want you to write down that we were trying to use the product rule. All right, and now I'm going to take the derivative implicitly with respect to time. You might notice I stopped writing the 1 times because it's easy to predict that that's happening. I'll use the power rule here, and I'll get 2 pi r squared times the derivative of r with respect to time. Okay, let's stop. Let's geek out here just for a moment. You might notice that this starts to look a lot more like a different formula here. This starts to look a little bit like formulas for spheres, and it's not exactly right. It has to do with a little bit with what's happening here with the h equals 2r, but you will sometimes start to see some formulas that are like, hey, that looks like something else a bit. Okay, back to it. So remember, we want to take the derivative of both sides implicitly with respect to t, and then we want to use substitution. And so I am now going to just go through and replace the variables with the known quantities that I've been given, 12 squared and times dr over dt, which is 3. And I'm going to end up with 864 pi, and then I've got to think about the units. Well, it's easy to tell that time is in minutes. But right here, keep in mind, this is the rate of change of volume. Volume is always units cubed, and our units for the linear unit of radius was inches, so this would be inches cubed per minute for the units. Units are typically a full point. A full point. All right, let's take a look at this next one.